Hello again. I'm going to try something different, which is not talking about the pipefish that I usually work with, which is Nerophis lumbriciformis. So I'm going to talk about Typhla again. So this is not just my work, it's a group of people, namely those from Eurosync here. So, and we are trying to look at, again, the influence of temperature on morphology. So it's so evident, the impacts of temperature from molecules to the functioning of ecosystems, that people started to see some trends. For example, the ones that everybody learned in school and immediately associates, which is as you go up in latitude, the size increases in fish, or the Bergmann's rule, or you go up in latitude and the extremities get shorter due to the cold. Okay, so these are the most known biogeographic rules, if you wish, linking temperature with morphology. So, and this works relatively well for some species. So with time, lots of exceptions started to being described, for example, in insects. And this shows that temperature is not the only factor that affects the morphology. Okay, so, and one of the problems with these ecogeographic rules is also that they focus too much on size. And as we know, or you should, size isn't everything. So this is a male joke, so a sexist male joke. So there's the problem with size, that these rules just look at size, and there could be variation in other things apart from size. And some of these rules also give us the notion that variation tends to be very linear. You go up in latitude and size increases or whatever. So we try to look at the data from other pipefish. This is the pipefish that I work more, which is called Nerophis lumbriciformis. And one of the things that we found is that, for example, it follows Bergmann's rule when we look at size. But if you look at other traits, there's no linear correlation with latitude. So some characters, for example, like body size or dimorphism, sexual dimorphism, are linear with latitude. Others, like the expression of sexual traits, for example, they have a U-shaped or a parabolic distribution. So I was interested to see this non-linear interaction between temperature and traits that we can choose to describe a species. So we looked at this species, Signatus typhla. This is a beautiful picture from Patrick, which is here in the front row. And we chose this species because within, well, if you look at the phylogeny of syngnathids, there's a clear division between those that brood on the trunk and those that brood on the tail. For example, seahorses and Typhla brood on the tail, the males brood on the tail. Nerophis lumbriciformis, the species that I told you that I work with, broods on the abdomen, on the trunk area. So there's this cool variation. And Typhla is interesting because if it broods on the tail, it means that there is space for different agendas between males and females. Because the ovaries, the gonads of the females are on the trunk, but males incubate on the tail area. So if there was some pressure for the species to produce more offspring, it would be more probable that females would elongate the trunk to have larger ovaries, produce more eggs. Okay. For males, it would be more probable that they would extend the tail to have larger marsupia and then have more kids. This is a very basic and probably not very realistic hypothesis, but it's something that we can use to test. So we've collected lots of pictures of pipefish. We have more than 1,200 specimens. I measured them all, and we focused on the trunk and the tail. So we did a proportion between the trunk and the tail. And for males also, I measured the marsupium and calculated the proportion of the marsupium compared to the total body size. And this is the distribution of the samples that we were able to gather. So basically what we saw is that they vary, the trunk, the tail, and the marsupium, they vary linearly with size, which is cool. But when you use these proportions, now you can see non-linear trends appearing. This is compared with temperatures. Okay? So forget latitude, now let's just use temperatures, and you see non-linear patterns emerging. And the cool part is that the extremes are more similar. Well, so when you have too much cold or too much heat, the morphology seems to be similar and different from the optimum for the species, which I found really interesting. So I got the temperatures of the seas, and I tried to see if there was some stage where there was a clear difference in average temperature. And we see that for the Atlantic, the Baltic, and the Mediterranean, they're heating up, especially during the last years. But around the year 2000, there was a step up, which was common to all these three seas. So we divided our data set pre-2000 and post-2000 just to be able to contrast these two groups. And what we saw is, one, the morphology of males and females is similar. So the proportions are similar at the extremes of temperature. So they have a U-like distribution. We saw that there is a difference between pre and post 2000, which means that in 20 years the morphology changed, and it changed significantly. So if you look at the top graph there on my left, you can see that the Mediterranean is particularly different. During the last 20 years, the Mediterranean changed a lot, significantly. So you see that the tails are getting smaller and the trunks are getting wider for males and for females as well. So they're responding in the same way. In the males, you can see that the difference goes up to France and the British Isles as well. If we look at the marsupium, so the marsupium is getting smaller on males. So in the Mediterranean, for example, we are seeing that. So this shows that the response is common between males and females, but this will impact the sex differently. So the trunks are getting larger, which could imply that females will have more space to develop their gonads, but the marsupium of the males is getting shorter, so they're getting less space to brood the embryos. A cool thing is, if you look at the Baltic Sea here, you see the Baltic Sea was on the top part of the cold, but not anymore, because the Baltic Sea is getting warmer. So the phenotype is getting back to the middle part of the distribution. So the marsupium is growing in the Baltic Sea. So, and all of this suggests that most of these morphological changes is due to phenotypic plasticity. In 20 years, you can measure differences in the development of this species. So as takeaway message, so museums are really important because they give us access to the past and to measure how species were in order to compare them to how they are today. We can see that temperature can reshape the body architecture, not just size. Okay, size is cool, but there are other things happening, and size may not show us all the information. So here we can show, we shown that there is difference in the architecture. A cool part, at least for me, is the convergency between the extremes of temperature, which thermal stress, independently if it's produced by high or low temperatures, seems to be producing the same end result, not just on this species. So in Lumbriciformis, the other species, I'm seeing the same patterns, which is strange, at least. It's cool to see that different metabolic pathways can produce the same phenotype at the end. And one of the things that I would like to highlight is that we can have these cryptic effects of climate change. So even though the two sexes are responding in the same way, the consequences reproductively will be distinct, but probably not very good for the species. Okay, that's my take on the morphology of Tifla. Thank you very much.